All right, now in part B it says the card is red given that it is a heart. So we're reversing this. So we're asking the probability that it's a red given that it's a heart. By definition, this is the probability that it's a heart divided by the probability that it's a red and a heart. Again, there's several ways we can think about it. The probability that it's a heart is 1 out of 4. The probability it's red and a heart is also 1 out of 4. It's certain that if you have a heart, it's red. If I know the card is one of these, I also know it's red. For part C, it says the card is an ace given that it's red. So the probability that something is an ace given that it's red. Is it red or heart? Red, okay. What's the probability that it's red? What's the probability that it's an ace and it's red? Well, probability of some card being a red is 1/2. The probability it's an ace and a red, well, there are 2 red aces out of 52. So the probability that you would have a card that's both an ace and a red would be 2 out of 52. And let's see, this turns out to be 4 over 52, which would be equal to 1/13. Another way of thinking about this is the following. How many red cards do you have? 26. How many red cards do you have that are aces? 50. That's also 1/13. So you can think of it this way or in this way. It's a consistent way of thinking. Now for problem number D, it says the card is a queen given that it is a face card. So, what's the probability that it's a queen given it's a face card? Face cards are Jack, Queen, and King. Okay? So this would be the probability that something is a queen and a face card divided by the probability that something is a face card. All right, in this case, if you're both a queen and a face card, let's see. So you've got 1, 2, 3, 4 cards out of 52, which are both a queen and a face card. These are kind of the, if you will, these two, queen and a face card. Well, a queen is automatically a face card. So that's 4 out of 52 divided by the probability it's a face card. There's a total of 12 out of 52. And so this is going to turn out to be 1/4. Oops, how about 1/3? That makes more sense. So if you know it's a face card, basically you know there's one chance in 3 that it's a queen.
So do you have to answer this, you have to have this picture in your face?
Yeah, you have to have this model, the mental model of this deck of cards.
So you just use the 4 divided by 12 to find 2, right? Because of 4 face card queen and total face card.
Are you talking about this here? This is invert and multiply. This is equal to 4 out of 52 times 52 over 12.
So you don't have to.
4 out of 12 is 1/3. This is why we require so much algebra. So you remember how to do divisions by fractions. You invert and multiply. Sometimes it just doesn't sink in. All right, now, yeah, you have to have this model of a deck of cards. That's what they're assuming. That's why I put this up in my overheads. Not all decks of cards are the same. Spanish cards, I think, have 50 cards in a standard deck. I think that's right. And then I don't know about other cards having other cultural origins. I think this is maybe French and English, something like that. But there are other standards, but this is the standard. When we talk about a standard deck of cards, this is what we mean here. Okay. Now the next question was on 6. Okay, it says a survey of students in a large introductory statistics class asked about their birth order, one being the oldest or only child, and which college of the university they were enrolled in. It says here are the data. So apparently there were 223 individuals who filled out this information. Of those, 113 were the first in their family or the only child, and 110 were from families where there were 2 or more. And the total in arts and sciences was 57. The total in agriculture is 93. Total in human ecology was 43. And all the others were in 30. So you have 223 individuals cross-classified, if you will, both by the college they're enrolled in and the birth order, whether they were first or the only child, or whether there were 2 or more in the family. Now it says, suppose we select a student at random from this class. What is the probability the person is a human ecology student? Well, there are 43 out of 223, so that would be the probability that an individual would be in human ecology. What's the probability that someone is a firstborn? All right. Well, that's 113 out of 223. All right. What's the probability of a firstborn and a human ecology student? Well, you need to look in the row and the column associated with that. The row associated with being firstborn the column is the first column. And then the row is the third row, so there are 15 if you will, individuals who fit the classification of both being firstborn and enrolled in the human ecology college. All right? So it would be 15 out of 223. Now, in D it says firstborn or. So there are a total of 113 firstborn. There are a total of 43 who are human ecology, but I need to subtract from that sum 15 because the 15 is being double counted and I don't want to do that. So it would be 113 plus 43 minus 15, all divided by 223.
May you explain the question number 20?
Okay, let me just, the questions on that.
Because it says and this is 113 over 2 times 15 over 3. I multiplied instead of.
Well, okay, the thing here is, and you can only take the, in other words, the probability of being in a firstborn and and being in human ecology, you can only take the product of those probabilities if they are independent, and you do not know that fact. So you must do it in the way that I have indicated. You would take 15 divided by 223. Now, if they're independent, that result should be 15 over 113 times 15 over 43, and I don't think that's the case. So strictly speaking, for this, in these individuals, they are not independent. Independence, you can take the probability if you have the probability of A and B is equal to the probability of A times the probability of B only if they're independent. And vice versa. If that, in other words, the probability of an event A and an event B may or may not be equal to the product of their individual probabilities. If this is the case, we would say A and B are independent. Or on the reverse side, if we talk about two events as being independent, such as when we roll a die twice, what happens on the first and the second are independent, then our probabilities are constructed by saying the probability of this is simply the product here.
I saw you talked about last week, you said that A given B equal.
Okay.
That's if A given B equal probability B, probability A, that means both events is independent.
Okay, let me write down the following. This result is always the case. Now, if A and B are independent, this is equal to this product, and I'm going to have cancellation. Okay, so you don't, in other words, this is simply a definition, and when you have two events, A comma B, are independent, then the probability of A given B is nothing more than the probability of A. Now, a nice way of keeping this in mind, or thinking about this, is if knowledge of the occurrence of the event B does not change our knowledge of the occurrence of A, then this is the case. And what I'm saying is, if that knowledge isn't passed, they are independent. Two events are independent. If knowledge of the occurrence of one does not change our knowledge of the occurrence of the other. You can think of a knowledge as being a probability. Before I flip a coin, before I know the results, the probability of a head is 1/2 and the probability of a tail is 1/2. So my knowledge is, well, I've kind of split the difference, so to speak. Now suppose I roll a die and I say, what's the probability, let's see, what is the probability as a 3 given that the number is divisible by 3?
What changes your chances?
Okay. Probability we observe a 3 given it's divisible. Well, if I know a number is divisible by 3, I have knowledge. My knowledge has changed about whether it's a 3. If I just take a die and I roll it, and I get some result, and I hide that result from you, what's the probability of a 3? What's the probability of 3? It's 1/6. But if I roll it, and I tell you the number is divisible by 3, basically I've given you information that changes our knowledge about whether or not it's a 3. Okay? So the probability of a 3, given it's divisible by 3, well, it's 1/2. You can go through the formal analysis, but this is 1/2. If I know it's divisible by 3, that means it's either a 3 or 6. My knowledge has changed with this information here, or with the statement that that event has occurred. If it's divisible by 3, it means it either was a 3 or a 6. I'm sorry, what did I say?
No, 1/3.
Well, okay. Oh, that's 1/3. Okay. Okay, divisible by 3. That's 1/3. What's the probability of a 3? It's 1/6. 1/6 divided by
1/3.
1/3 is 1/2. So this answer is correct. I'm not sure what I mean, if you know it's divisible by 3, well, you know it's either a 3 or a 6. So you know the probability is a 3 is 1/2.
1/2. Half over 1/3 is 3 divided by 2.
Okay. The probability is 3 and
divisible by
divisible by 3 divided by the probability that it's divisible by 3. The bottom one, divisible, that's 1/3. What's the top one? Well, if it's 3, it's also divisible by 3.
1/6.
1/6. 1/6 over 1/3 is 1/2. I think what I want to do, I would take problems on 16, but if they're more on 15, I'll be happy to do them after class, because we need to move on. Are there any problems on 16 I should address?
We don't have 16.
16,
I don't know.
Okay.
You don't have 16 now. Number 15 don't have 16.
No, I'm talking about
Oh,
problems
chapter
on
15.
chapter 16. If you have questions on 16, I'll take those now. Otherwise, I want to move on. Okay? The chapter homework commentary, I didn't have answers for problems 2, 4, or 6 in chapter 15. That has been corrected, okay, so as of last night, late last night. Now, in all those problems 2, 4, and 6 in chapter 15, I indicate you should draw a Venn diagram, something like I was doing for the, well, let's see, the France, but in 2, 4, and 6, it's just 2 events, all right? And think of them, the overlap, all right, and how those questions relate to what portions. In other words, when you have a question involving a Venn diagram, let me sketch a Venn diagram where there's an overlap. So in those problems, you've got 2 events that overlap. So we'll call that B, the red part B and the black part A. Basically, the question is asking sometimes for the A with this chunk taken out, sometimes it's asking for B with this chunk taken out, sometimes it's asking for the common portion, and sometimes it's asking for what's outside. And I think it will help you to understand the nature of the question by drawing something like this, and then saying, okay, A represents one description. B is another one, and some of those descriptions will overlap. And note that the sum of everything, over the whole space, the probability is 1 or 100%. And so it's a matter of kind of doing the bookkeeping associated with a diagram such as this, where there is overlap. I think that's the easiest way to approach this.
So, A and B are negative 1 or
The total thing inside the rectangle is 100%. Okay, and A is some subportion of it, or an event. B is some subportion or an event. And there's some outcomes, if you will, found in the sample space that are both in A and in B, as I've described it here. Now, A and B may or may not be independent. You cannot tell from this diagram. On the other hand, if you have something like this, where there's no overlap, they are not independent. Why is that the case?
That's just wrong.
They have nothing in common. So if I tell you A has occurred, I know automatically B has not. So here they are disjoint or mutually exclusive. And in that case, all right, they are also dependent. If I tell you B has occurred and this diagram is appropriate, I know A has not. And these diagrams I have up on the, in a file on the website. Yes?
Can you give an example for the top one of when A and B would not be independent?
The only way you can tell that in this case, so to determine if A, comma B are independent, what we do is we check, is the probability of A and B, is that equal to the probability of A times the probability of B? So you need to know these two values here, and then you need to use this knowledge there. So this right here, use another, this common portion is A and B. So if you can figure out the probability of this common portion, put it in here, is it equal to the product of this times the probability of B, which is what I have here. If that is the case, then they are independent. Now, this is the appropriate way to look at it when you're given effectively a Venn diagram or something equivalent to this. On the other hand, if we do something repeatedly, we can claim something as independent just by knowing how we're doing it. Tossing a coin, the result on any toss is independent of the result on any other toss. Rolling a die, the results on any given roll are independent of the others. All right, and then now in drawing a card from a deck of cards, it depends upon whether or not you're putting the card back into the deck, which is called sampling with replacement, or you are not. If you put a card back into a deck and shuffle it again, you're exactly the same place you were on the previous draw. Whereas if you draw a card from a deck of cards and leave it out, which is sampling without replacement, the next time you draw a card, your knowledge has changed because you know that one card or all the cards you've taken out can no longer be selected. Okay.
Can I ask one more? You said that the top one is disjoint?
No, they're not disjoint.
They're not disjoint.
This is disjoint, this is not.
That's the bottom.
The bottom is disjoint. So this is, in fact, let me pull up that Venn diagram. Okay. These are disjoint. All right. They have nothing in common. These are not disjoint. They have something in common. I know these are dependent just by the drawing itself. I don't know that in this case. In this case, to find out whether or not A and B are independent, we need to see, is this equal to this product? Now in 244, we're going to break this rule slightly when we talk about test for independence. And it has to do with how we think about the data, if you will. So if you come back for a second round in 244 and we get to test for independence, we'll be using something called a chi-square distribution. And we'll be using a test to see whether or not our results suggest independence or not. In this case, we're not doing statistical analysis per se, we're simply laying the foundations for probability. So if you're not coming back for 244, that can be stricken from the record. All right. Let me bring up my overheads again here. And let's see here. I want to emphasize something from last week when we were talking about medicine and how I was using Bayes' rule to analyze what is the meaning of a positive result. Please be advised, this is not a class in your health. This is a class in probability. Your doctor should always help you make these decisions, all right, as to what tests you have when you have them. When you get older, of course, that doesn't apply to anyone here except maybe one person. They invent more tests for you to take, okay? All right? And when you take them, I mean, usually your doctor's going to say, look, you know, you're getting to that age, all right, when you should have this test. You should start thinking about having this. All right? And that's where, if you will, the rubber hits the road, where your doctor uses his knowledge of medicine, uses his knowledge of your particular circumstances, and then suggests when you have tests. All right? And the thing is, medicine is always changing. You know, when I was, until I was well into my 30s, you probably couldn't get an MRI, a magnetic resonance image. I mean, the technology was just being developed. And now today, you're willing to put down, I don't know, somewhere between 1,000 or 2,000, depending upon who's paying for it. Your insurance company will probably, or you, will have to pay somewhere between $1,000 and $2,000 for an MRI. For a CAT scan, I don't know what the prices are today. I would assume it's somewhere between $500 and $1,000. Again, you might have to pay for that, or maybe your insurance would have to pay for it. And in the case of MRI, at least so far as I'm aware, to date, they still have not identified any negative consequences or anything really significant about the test itself. You don't want to have any metal implants. You don't want to carry around tools in your pocket or watches. The watches will probably be ripped from your hand, or you'll be drawn right to the magnets. But aside from that, an MRI is a relatively safe test. Except when you go into the tunnel and if you have claustrophobia and you don't know it.
Uh-oh.
Okay. CAT scan is a different ballgame altogether. In a CAT scan, they expose you to X-rays. All right? And a doctor has to decide, is the risk associated with exposure to X-rays worth the price of doing a test and finding out something about you? Now, if that is scary, that you might be exposed to X-rays, then for forbid, they'll never take a flight across country. Because when you take a flight in an aircraft, you're exposed to gamma rays, or actually cosmic rays, which includes gamma rays and X-rays. And the further up you are, the more exposure you get. And I once heard of this, and a flight across the country is roughly the equivalent to a dosage of one chest X-ray.
Oh, wow.
Or a dental X-ray? Okay. Oh, they are. Oh, they do, yeah. Now they shield you. Now that it doesn't make a difference. So, I mean, that's what. Now, your doctor may not necessarily know about Bayes' rules in a kind of operational sense, but they would know about it from their practice. Okay, some of them will probably. Okay, so this is the purpose of doing an analysis based on Bayes' rules to see how it is applied. Now, let's go back to Bayes' rule just for a moment. This is a statement of Bayes' rule, and basically we're talking about two events, A and B. In Bayes' rule, you need to know the probability of B, and once you know that, you know the probability of the complement, because the sum of those must be 1. Sometimes those are easy to determine, and other times these are guesses. All right? That's the challenge in using Bayesian analysis, is knowing what this is, or having a good estimate of what it is. I think in economics they say there's no free lunch. In software they say there's no silver bullet. Why is there no silver bullet? It's all hard work. In software, I mean, I'm trying to think of the names guy. He wrote a book called The Mythical Man Month, which was his experiences in developing software in the 1960s. Still a very relevant book. Statistics is not a silver bullet. It never was, and it never will be. It doesn't matter what you do, how you do it.
Fred Brooks.
Pardon?
Fred Brooks.
Yes, Frederick Brooks, yes. I don't know if he's still around. But the point is that statistics is a tool, and regardless of which part of statistics or which assumptions you make, you still need to think.
Yes, he's 83. He's 83.
83, and he's still around? Okay. I'm told he's quite a chauvinist, too.
Probably.
Yeah, at that age. They tempered it by the time they got to me. No, it's been beaten out of me. I gave it up with great reluctance, but it was beaten out of me. No, it wasn't beaten out. And the same thing is true about what in statistics, if you do it the more traditional way, which is the frequentist approach, or you use a Bayesian analysis, you still have to think. There's not a simple answer in looking at data. And in the case of Bayesian analysis, is what is this value, and consequently, what is this? How well do you know that? And are there things where you can increase your knowledge of these by better defining what your probabilities are? And again, in the last 10, 15 years, Bayesian analysis has become more popular, but you should never take away from that it's a silver bullet. There is no silver bullet. There's no simple answer to anything. If you don't learn anything in this class, learn that there's no simple answers. Except unless I give them in class. Well, not even then. All right. I think last time we were talking about random variables. a random variable, we can think of it in several different ways. It's a quantity whose value depends on chance. If I roll a die, the top face can be anywhere from 1 on up to 6. So rolling a die produces the numbers 1 through 6, and I can think of that as being a random variable. And I represent a random variable typically by a capital letter X, which I can then use in algebraic statements, all right, where I then add it to either other random variables, what have you. Another way of thinking of a random variable is a process that produces numbers by chance. Again, this is an example. Your calculator is an example. If you do experiments in your science classes, your chemistry classes, when you're measuring pH or whatever it is you do there in your physics class, when you maybe measure temperature, resistance, who knows what, or in your biology when you're, I don't know what they measure in biology these days, but we can think of the number that we observe as a random variable. Now, some of these random variables have very nice structures to them. Okay? Case in point. I know exactly what I'm going to observe. Typically, when you do an experiment in physics, you have some idea of the range of values you're going to pick. But you never know exactly what you're going to observe. Now, there are two types of random variables. One is called discrete. When you roll a die, you can only observe, in a case of a 6-sided die, when the numbers 1 through 6. Discrete, at least as I use it in this class, means a finite number of values can be observed. Now, if you were to take additional courses, you would also discover that the Poisson process, or a negative binomial random variable, those are discrete, but they have an infinite number of values. Or the exponential function, 2 has, no, I'm sorry, negative binomial can have an infinite number. An exponential probability or model can have an infinite number of values. When you have an infinite number of values and it's discrete, it means the numbers 1 or 2 or 3 or 4 and so forth. But in this class, to kind of simplify matters, I just say something is discrete. When I use that term, it means only a finite number of values. All right, now, in contrast, a continuous random variable can take on any number whatsoever between two limits. So if I throw a dart at a dartboard and I measure the distance from the center to where the dart strikes, that's an example of a continuous random variable. It can take on any value from 0 on the way out to plus infinity. Well, not plus infinity. Usually you can't throw it that far, but it can be any number within a broad range, all right? And the measurement is only limited by the devices you have at hand.
So what is an example of a discrete random variable? Oh, that you said that, sorry.
A die is discrete. It can be 6-sided. It can be, have I passed around my 100-sided die?
I think we had a fire alarm then.
I think this is 100-sided. Please return this. It's and this one right here. Let's see. This is what, a 22, 24, 26. I don't know. 29. Maybe a 32-sided die. I don't know. Remember, those are my children, so don't run off with them. Don't kidnap them. Okay. Random variables are denoted frequently, but not always, by capital letters. I think I defined the expected value of a random variable. So there's a certain quantity that I can compute from a random variable. Sometimes I use the expression the expected value of the random variable, and sometimes I use the expression the mean of x. For a discrete random variable, it is computed by taking every value that I can observe and multiplying it times its corresponding probability. And then I add all those results, and that's what is meant by this symbol or that symbol there. I think I went through a computation of this last time. Now the variance of a random variable, which can be expressed symbolically in this fashion here, VAR, or using the Greek letter sigma with a subscript of x and an exponent of 2. Those two symbols represent this quantity here. In this quantity here, I take every value that I can observe, and I subtract from it the mean for that random variable, this being defined by that equation there. That difference is then squared, and then I multiply it times the probability of observing that value. And then I repeat that for all the other values in my table. Now the variance is always going to be a positive number, because we're squaring and probabilities are always positive. The mean could be either positive or negative. All right, now, a nice way of thinking about a random variable is a device that produces numbers for us. This is such a device. On my calculator, there's a function or a key there called, let's see, on mine I think it's called random. It may be on your calculator, it may be RAND or it may be RND. Now if I press on mine, the first time I did it today, I got the number 0.144745788 and so forth. If I enter it again, well, this time around I got 0.857 and so forth. This is the device that produces numbers between 0 and 1. Okay?
You said 0 and 1 is a variable.
Well, it's the range. In other words, this is we can think of this as being a continuous random variable that produces numbers between 0 and 1. We can almost think of throwing a dart along some sort of, line segment, and where the dart strikes between 0 and 1 is the number that's reported. This is a nice metaphor, and in fact, when you go to random.org, actually that's what they're doing for you there, is they're just giving you the results of actually a fairly complicated process electronically where they measure atmospheric noise. I think that's how they describe it. And they just report the results to you. You don't need to know the internals of how it works. All right. Now, once I have a random variable, I can create new random variables from that given random variable. And I'm describing one here. Here I have a device, an outside device. It has a button, and when I push the button on it, I get a number on the outside. I observe something. Now, in this random variable, the way it's been constructed is I have two fixed numbers. They're kind of stamped on the inside. They remain fixed. Those two numbers are referred to as A and B. Now, when I push a button on the outside, that in turn pushes a button on a random variable on the inside, which produces some number. That number is then multiplied times b, and then we add that to a. That's what we observe. Symbolically or algebraically, we would write y represents the whole thing, is equal to my constant a plus my constant b times my random variable x. So if I have a random variable x, I can create a new one by using constants a and b. I can create a lot of them. I mean, I could create one where I simply square x. That would be another one. But we don't go down there because this is the type of analysis or type of models we want to keep in mind. Okay, now suppose I have two random variables. I have two calculators, or I have two dice, both of which produce numbers by chance. I can create a new random variable which I'm designating by the letter W. We can think of that as device as being constructed in the following way. The outside device, I push a button on it. Internally, the buttons on these two devices are pushed. Numbers are produced which are then added, and then it's the result of the addition of those two numbers, which is what we observe. Algebraically, we write that W, which is the result of the whole thing, is simply the addition of what we observe for x and y. Now, both in this case here, and in this case here, if I know the probabilities associated with these numbers here, say, I can figure out for all the numbers I can observe over here, the corresponding probabilities. I'm not suggesting it would always be easy, but you can always do that. In this case, it's relatively easy. In this case here, if I know the table, if you will, associated with x, and the table associated with y, and maybe I might need some additional information, I can tell you what numbers I can observe over here, and I can tell you what probabilities. Now, typically in this class, in this analysis, we assume that these two random variables are independent. But it doesn't have to be the case. When they're independent, it's actually fairly easy to determine the probabilities associated with the values of W. If they are not independent random variables, okay, then it takes a lot more sophistication. Independence can be thought of as in the following way, or dependence. If there's dependence between them, there's a little signaling device between them. And it kind of changes what you see. It's kind of fooling you in a way. Whereas when they're independent, there's no connection between them at all. There's no knowledge that's passed from one device to the other. Now typically, but not always in statistics, we assume these two devices are independent. All right, now, I think I got to this point here. Let me ask the question at this point. Do we need a break? Because we need a break. All right. What I'm going to do when we get back here is the following. I think I went over these rules the last time. Again, these rules come from the devices I just talked about constructing. All right. And these would be theorems, if you will, in probability. I'm simply going to state them as facts, and then we're going to utilize them actually probably a little bit later today, even though it won't be obvious we're using them. All right. So when we come back, I'll pick up on this slide, and I'll talk about what the rules mean and how we employ them. All right. So I have about 5 minutes after 10. So let's take, I don't know, do we need a 15-minute break? Okay, so then at 20 minutes after, by my watch, 15 minutes, we'll resume. Oh, yeah. Yes, it will be.
How far will the next exam?
Through 16.
Through 16?
18 through, or 8 through 16, yeah.
And are there practice
We didn't
exams?
drink the water here, right?
You have to look through all the exams because they don't, the exams I have don't necessarily match exactly the chapters. But there may be, for example, problems on the final that would be relevant to some of these, yeah.
So up to 16 years old.
Yeah.
Perfect. Thank you so much.
Did you meet Elf? My friend?
Yes, I
He's
did.
really tall, huh?
Yeah, real tall guy, yeah.
He's super nice.
Right?
He's super nice.
It's very interesting. He wants to be a nurse.
His son is a doctor too.
Oh, is that right?
Mhm.